Let's start with our webinar, the third in our series of Zoom on Science. I have the pleasure today to have Sandra Luber here with us, and we will discuss a little bit with her about her science, her experience at CSES. I will introduce Sandra, and then she will talk to us. So thank you, Sandra, first of all, for accepting our invitation and having spent some time to talk to us. So Sandra Luber is a professor, SNF professor at the University of Zurich. She did the diploma in chemistry in Germany at the Langen University. Then she did a PhD at the TH Zurich. And she did a postdoctoral. She had a postdoc at the University of Basel, then in the US at Yale. You have a long CV, even though you are very young, in the US. And then she came back and got a project group leader position at University of Zurich. And then after her habilitation, she started as SNF professor at University of Zurich. And this is currently the position that she holds there. So welcome again, Sandra, and thank you for joining us. I will start with the first question. I will start with a few first questions, and then maybe there will be also questions from the staff and from the audience. So, Sandra, first of all, you have been a user of CSES for quite some time now. I mean, you have a number of projects with us, but also since quite a few years that you are applying for resources at CSES. But it would be nice if you could explain it to an audience of non-expert. What is the main focus of your research?
Yes, sure. First of all, thanks a lot for this kind introduction and the invitation. It's a pleasure to be here. Yes, of course, my research is theoretical and computational chemistry. So I'm also here at the Department of Chemistry. So our focus is on methods, first principles methods. So that means methods derived from quantum mechanics. So we have a bunch of different methods, one very accurate one, wave function-based methods, up to density function theory, which is a quite popular method. And also beyond the static approaches, which are many used in quantum chemistry, usually also dynamic approaches, so density function theory-based dynamics or quantum Monte Carlo. And the systems we are interested in are quite broad, so it can be molecule in gas phase or liquids or molecules absorbed on a surface or just surface in general. So there's a quite broad mixtures of applications we do.
So, okay, you mentioned quantum mechanics and quantum chemistry. So now I ask you a very basic question. So, what is the focus of quantum chemistry and quantum mechanics in general? What are these? What is the interest of a quantum chemist, and why do you use quantum mechanics to study whatever you study?
I'm focusing on quantum mechanics. Not Newton's classical mechanics, which would be a kind of a strong other direction, because I want to have a very accurate, detailed insight into certain molecules or larger systems. So that's why I'm more started focusing on this quantum mechanical methods.
Yes, thank you. That's very nice. I mean, so you use these methods because you are interested in very accuracy of the calculation or the simulation and the results that you get. Very good. So how intense how compute intensive is your research, and why is compute intensive? I know that you need a lot of resources to run all your simulations. So why is that?
Yes, a very good question, of course. Yes, so I mentioned this ab initio molecular dynamics, and this is a quite expensive way to do dynamics. So usually it's using density functional theory for describing the electrons. So we have to do it a lot of different times, computing energies and gradients. And of course, if we want to do dynamics, we have to also have a certain length of the trajectories. So we need a lot of computations, the snapshot computations, in order to make a reasonable statement about reaction pathway using enhanced sampling methods or computing spectra. So this is a very computational expensive approach, but of course also a very accurate one. So one gets much more insights than just doing one static calculation, which of course is less realistic than doing really a dynamic calculation where you can sample, for instance, all the different conformations of a molecule, and in a liquid there are a lot of different interactions which are otherwise really difficult to capture. So that's why we use a lot of computational resources at CSCS. Yeah.
You are you are a theoretical chemist and a computational chemist. But my first question would be: do you have collaboration with experimentalists, or is your a purely computational research that then it's published? Of course, you publish a lot. I know that. But do you also have collaboration with experimentalists?
Yes, we have, of course. I mean, this makes the research much more interesting, because otherwise maybe the danger is that one gets lost in improving certain parts of a method, but in the end one does not know what it's really useful for in really interesting applications. So yes, we have different collaborations here at the department, or also international ones. So for instance, we have here this university priority program, which is called Solar Lithochemical Energy Conversion. And there are a consortium of different experimental and theoretical groups work together to develop a water splitting device, which is for basically generating hydrogen for energy storage and conversion. So this is
So you would be also one of those that would have an impact in car moving with a hydrogen based technology. I'm just giving an example, or is some different kind of application? Because I heard, I recently bought a car, so I've seen all the new technologies available for the cars, and there were also some samples of cars that are moving with this hydrogen based technology. But what are the other applications that would be also interesting from regular, for a citizen? Why is important to have this kind of studies?
So what we are focusing on is generation of hydrogen. That's true, but we want to use sunlight for it directly. So often at the moment, basically, it's kind of going an indirect way by, for instance, using power generated by sunlight or wind to make electrolysis and then generate hydrogen, which you use further. And we want to do it directly using the sunlight without going the steps-wise this additional electrolysis. So this is basically the idea of this approach. And also, of course, it can be more efficient in that sense, because you have you lose less on the way, basically. And of course, hydrogen is very attractive, not only for cars. It's also interesting, for instance, to further to combine it with CO2 to generate new hydrocarbon molecules, methanol, methane, etc., which are important chemicals for industry, for instance. So there's a broad range for this hydrogen beyond just using it for cars.
No, sure. I give you an example because no one came up to my mind, but of course it's not the most obvious one. I totally agree.
Yeah,
totally agree with you. It was just, as I said, I recently were buying a car, so I was exposed to these new things that are coming out besides the electrical car, of course. Very good. Thank you very much, Sandra. Now as I mentioned, when I introduced you, you have studied in Germany and then you came in Switzerland where you did your PhD at ETH Zurich, and then you went to the US and came back, and now you have a professorship position there. I would like to also to know you a bit better. So what triggered your interest in science? Why did you decide on this career?
Yeah, so it's a longer story.
Yes, please.
And also what not always obvious. So I tried a lot until it came clear to me that maybe I want really to go to an academic career. So maybe I tell a bit how it came. So yes, I basically went to a school which was focusing on music. So it was actually less natural sciences than usual at school. I really liked it. I liked music. I liked Latin. So yeah, but somehow I thought, what should I do in the future with that? So when I was finished my A-level exam, I had not much clue what to do. So yeah, I got the advice to study administrative sciences because then I can go to administration. It's a safe position, especially for women, and if you want to have kids and so on. So I decided to do that, but after half a year or so, it was nothing for me. It was not fulfilling. I was also sick, which I've not been before, so it was really not fitting to me. And then I somehow thought, let's do something which is kind of basic and kind of accurate. And then I decided just quite spontaneously, let's change to chemistry. So I started chemistry. Then I was in the lab with a tube, which I had never in the hand before. And it was quite frustrating because the analysis was not working, the synthesis was not working. So it was for me quite frustrating. And I thought, I want to understand it more in detail, what's going on. And in that way, I came more to theoretical chemistry because I had a feeling it's exact and you know a bit more what you are doing. So.
Was your diploma thesis already in computational or theoretical chemistry, or you did was just at the time of your PhD that you went more in depth in the theoretical chemistry?
No, it was already a master's thesis. So I came as an exchange student to ETH, and then I got convinced that I should stay at ETH. So basically, I did the master's also at ETH then. And there was already, my master's thesis was already in quantum chemistry, and I did also PhD then in quantum chemistry. Yeah. Very
good. Sandra, you are a woman in a world that is considered still very male-oriented, in the sense all these STEM science, technology, engineering, and mathematics are considered, maybe not at the university level, but for a career are considered more like male territory than women territory. First of all, do you agree, or your experience has been completely different in your course of studies, where there are equal number of girls and boys that studied these subjects?
I think on average there were more men than women. Yes, I would agree in that sense.
And do you believe that? First of all, do you believe that this is still the case? That is still very, still dominated by men, the field, or now that you are a professor, things are a bit better, changed, or are changing? What is your feeling? If you have, observed a little bit, I am interested in this topic. This is why when I have a guest, women guest, I always ask these kind of questions.
Yes, I have the feeling that it's changing a bit. I mean, from the people who studying chemistry, for instance, there's not so much difference anymore, I would say, but the difference becomes more and more obvious higher you go in the career level, so PhD postdoc, and then afterwards it's really big difference between women and men. So somehow we lose the woman on the way to the top. But there are really now a lot of new professorships, these tenure track professorships, in Germany also junior professorships, which are also filled with women a lot, as I can see from here. So I think it's improving the situation. So people really try to promote women also on that stage of their career.
And do you have many students, female students, that they apply, for example, to do the PhD with you, or a postdoc, or a diploma thesis, Semesterarbeit, or whatever that is, or not so much, or still not enough? Let's put it this way. Still.
No, unfortunately, not so much. So still mainly men. I have the impression that the women are mainly more interested in doing lab work. So theoretical computational chemistry is maybe
not attractive enough.
Yeah, I don't know.
Did you have to face any specific challenge during your career just because you were a woman? Have you ever experienced anything as such? Or you think that, no, it went basically as you wanted without any special drawback or whatever, any special impact due to the fact that you were a woman rather than a man?
Yeah, I'm not sure. It's maybe a bit difficult to say. I mean, there's some situations where people try to show that you are kind of incompetent or something like that. So I'm not sure if it's because of a woman, or maybe it also happens to other men. So I'm not completely sure about it. But yes, I had experienced several such situations. So maybe it's a bit more in case of women than instead of men. But it's difficult to say.
As I said, it's just your personal feedback. I mean, it can be, can also, you could also not have experienced this, and that would be perfectly fine. It doesn't mean that it doesn't exist anyway, but that's fine. So Sandra, I know you've had a number of projects at CSES, and I know that you have also been interested in the catalysis. And I'm bringing this up because the Nobel Prize for Chemistry this year was awarded to Benjamin List and David Macmillan for development of precise new tool for molecular construction, this organocatalysis. I would like you to explain to us in simple words what is catalysis exactly?
Yeah, so catalysis is if you have some molecules which you want to react to a certain product, usually have to overcome a barrier to form the product. And catalysts can help in the reaction by lowering the barrier so that the reaction takes place easier. And this catalyst itself is just helping, but in the end of the whole reaction, it's basically the same as before, so it's always regenerated.
So you want to go from a molecule A to a molecule B, but you need some help. Mm-hmm. And this help is this catalyst, which is yet another molecule that will help the reaction going in the direction that you want it to be. Is it a fair simplification of,
yes.
Okay, yes. So very good. But that's thank you for that. But first of all, what do you think about this Nobel Prize? Did you maybe it's not precisely the same kind of study that you do, but do you think it was well deserved? And what kind of catalysis studies are you doing in your own research?
I think, this contribution which was made by these two Nobel Prize laureates, yes, I think it's very well deserved. I mean, they were awarded for asymmetric organocatalysis, which is basically based on organic molecules, which are usually based on carbon and hydrogen atoms and some other atoms. So not metal atoms would be different. And asymmetric means like you have two molecules which are spatially oriented in a different way. So the composition, basically the number of atoms is the same, but they behave like a hand and the other hand, so like a picture, image and a mirror image. This is exactly what they have been basically improving with their organocatalysis approach by just using simple organic molecules and not toxic metal complexes or something. And we now mainly also for the water splitting catalysis, we are usually based on transition metal complexes. So we deal with metals. So we are not using organic molecules for that. So also can be more challenging also in terms of some theoretical methods you should use. Yes, that's maybe, and then we are also not so much interested in asymmetric catalysis, because this does not play any role for this water splitting catalysis. So we are not interested in this mirror image thing.
Images, yeah, very good. Sandra, may I ask you, how did you choose your path? I mean, this field of science, was this by chance? Was this because you started in your PhD and you were very excited by it and you wanted to continue? How does a scientist, or more general question, how does a scientist starts his field of research, and what is the idea that triggers a specific interest?
So my research field are somehow have evolved over time. So spectroscopy has been already interested since my master thesis, basically. So just expanding with methods and type of systems we are looking at and developing new approaches. With this water splitting was quite fun. It was by accident, because when I was in Basel doing a postdoc in bioinformatics, it was quite different. I got an email from Yale asking me, do you want to join us at Yale? And then I was Googling, what does this group do? And then I saw it works on photosynthesis. So doing basically similar water splitting, so water oxidation, which is involved in water splitting in nature, in the photosystem too, which is in the plants. And I thought, oh, this sounds very interesting, let's do that. So I changed to Yale, and somehow with that I got the first touch with this water splitting catalysis, but only in the natural system, in the plants. And then I went to BASF for becoming an intellectual property lawyer, which was, again, not really fulfilling. So I changed back to the University of Zurich for doing the habilitation. And then I came here and started my research, and I had no clue about this priority programs that we want now to develop an artificial water splitting device. So at some point I was asked by a colleague, we have seen your paper from Yale, can you help us? We have now this artificial catalysts for water splitting, can you help us? And then I was immediately again in this water splitting direction. And it's very fascinating. There's still a lot of things to do. It's also very challenging from the method point of view. So I really like it. And also with the collaboration, there's a lot of input also from the experimentalists. So I really enjoy this research environment here. So I'm quite happy.
So it's still a very exciting field for you, and there is mainly, if I understand if I get your message, there is still a lot to do. There are still a lot of ideas that can come up, and new interesting questions to be asked and to be answered.
Yes, so we are still looking at the very basics to understand things, but of course we want to be better, and also the catalysts are often not stable, which is important also for industrial use, and also scalability to larger, more amounts of production and so on is still a problem. So yes, there are still quite some open points to look at. So
they need to be addressed. I don't see anybody, but are there questions from the audience? In this new setting, I am not fully, otherwise, please, I think you can unmute, or maybe someone can, yes, let me see. I can unmute. If you have any question, please raise your hand and I will unmute you and you can ask the question. Oh, yes. Michele, please.
Mute. Perfect. Hi, Sandra. Thank you for sharing with us so many informations. Menegrasa, she took an example about hydrogen and the usage of hydrogen. And, she was using it only as example, but when I was a child, now I'm getting older, 57, and there was always said that the future is hydrogen. And now we are still saying the future is the hydrogen, but we still don't see really good usage of hydrogen. Is this because of, and is, in fact, the simplest element chemistry does has, so I think going down there is, we cannot have less. So is the problem related to technology and the economy? They don't really want to use it? Or do we still have so many questions related to science about such a simple element like hydrogen? I have the impression we are not really moving anywhere there.
Yeah, thanks for your question. A very good point. I think maybe it's part. So as I mentioned, for this directly solar light-driven water splitting, which we are trying to develop here, there's still a lot to do, still on the basic side. But yeah, for this hydrogen-driven cars, where you make the indirect way by using power generated from sunlight or wind or whatever, and do this electrolysis, I think that's maybe just also still is needed to build the infrastructure. I mean, you need to fuel your cars and everything, and also transport hydrogen, which can be also quite challenging. So it can be explosive. So I think the infrastructure is also still missing. Yeah, so I guess that's two main things which come to my mind for that.
Other questions from the audience? Raise your hands, and I will. If I see a hands up, I will give you the floor. While we're waiting, Sandra, okay, you know, we are already starting to put in place a new system. That we have put the first four cabinets, and this new research infrastructure will be called ALPS, but we are still a couple of years from having the full machine. So do you have a problem in your drawer or in your virtual drawer that you cannot take it out because you don't have enough computational resources and maybe storage to actually address it? Because this is a common questions that we are asked. Why do we need always a newer system and more compute power? And this is the question that I usually then transfer to the scientists themselves. So why do you need more resources, or would you need more resources to answer some scientific questions, do you think, in the near future?
Yes, I mean, we do a lot on the density function theory basis at the moment, but especially for this transition metal complexes, it can be very challenging. So you need to go to more accurate approaches, and here they become very fast, very expensive, also memory expensive, depending on which approach you are using. And if you would have more computational power, I would maybe use more quantum Monte Carlo or so to really solve the electronic structure in a very accurate way, where we can also see, for instance, how electron spins are oriented and so on, which can be quite challenging and not so accurate with DFT. So yes, I would for sure use this computational power to go even deeper into the electronic structure of this complex.
I mean, I know that you use a lot of computational resources because you submit also multiple projects, so you need the resources. I don't doubt that. So, but you are telling us that you would have problem, or you would be able to use more computational resources if available for improving your studies and your research.
Yes, for sure. So at the moment we are still limited in the size and so on. Yes.
You have used many times this density functional theory. This is a method that you are using. Would you be able to explain very simply why is density functional method interesting? I mean, what is the base of a density functional method, if can be explained to an audience that is not necessarily into theoretical chemistry and quantum chemistry? What is the characteristic of such a method? What are you interested in? What are you look at with this method?
So as the name says, it's based on density. So it's based on electron density, which is different to the original, more conventional wave function-based methods, because there are much more variables to integrate over and so on. In density, you have less variables, and it's more efficient, for instance, to solve the Schrödinger equation, also with the Kohn-Sham approach, which has been very successful. So basically, we want to solve the Schrödinger equation in an approximate way by relying on the density as the main variable, which simplifies many things and also many integrals to calculate. So it's quite efficient.
So it's a method to solve the Schrödinger equation, but it's still in an approximate manner. So not in an accurate super. I don't think that's the case. But yeah, are there other questions from the audience? I don't see any. Raise hand. No, but then maybe Sandra, I will close the discussion and the webinar here. If there is no other question from anybody, I want to thank you very much for participating. The Zoom on Science is meant for knowing our scientists better. Maybe I would have a very last question for you before saying goodbye. So you have been using CSES since a long time. So what, if there is one thing, I don't know, I won't ask you what do you like about CSES. I would ask you the opposite. So not what you don't like, but if you would ask, if you would want to improve something in the way we offer our services, what is that you would like to be changed or to be improved, or from a scientist point of view, so from a user point of view? You can be honest, you can be as open as you as you like.
First of all, I really like it, and also the service is really very good. So what is sometimes a bit unpractical for us is that the queuing time, for instance, is limited to 24 hours. So this is something for certain programs, and restarts not so practical. Yes, and of course, focusing more and more on GPUs might be not so easy for certain codes if they are not so well adapted yet to GPUs or not so efficient yet on GPUs. This is also one point, which one has to see how it will develop.
Do you a lot of your research is done with codes that are not able to use the GPUs?
I mean, we use a lot of CP2K, which partly can use GPUs. So yeah, as I say, partly the QMC code is mainly based on CPU at the moment. Yeah, it depends on the code and the method.
On the problem that you want to address, of course, that's very clear. Because also with when the new big complete Alps will be installed, this will be still mainly accelerated system. So we are not really changing the direction, but maybe there must be a more coordinated effort to port more of these codes on accelerators, because this is not only Switzerland, actually also Europe is moving in that direction. All these big new pre-exascale systems are based on GPUs for different kind, but still GPUs. But I think the direction is still, the path is still accelerated. Okay, so thank you very much, Sandra. I'm very happy to hear that you are still happy with us. There are still that we can improve, absolutely, always. I'm very well aware of that. But unless there are some very last question from the audience, which I don't see. No one is raising the hands. I thank you very much for your time, Sandra. I appreciated a lot this informal chat. And I wish you all the best for the next project that I'm sure you're going to submit at CSCS. Thank you very much.
Thank you very much. It was a great pleasure. Thanks a lot.
Ciao. Bye-bye.
Ciao, ciao.
Thank you all for participating.
Thanks.
Bye.
Bye-bye.
Ciao.